Hello friends, ladies and gentlemen, welcome to the Raymond Nicolet Trust Podcast. My name is Gavrilo Nikolic, and every month I bring you inspiring conversations about the future of education, science and philanthropy from world top academics, scientists, Nobel Prize winners and philanthropists. My guest today is Dr. David Kent. Dr. David Kent earned the BSc in Genetics and English Literature at the University of Western Ontario in Canada, and later obtained his PhD in Genetics at the University of British Columbia as well in Canada. His postdoctoral research was at the University of Cambridge, where he primarily studied malignant blood stem cell biology and established his research group in 2015. In 2019, the lab relocated to the University of York and the York Biomedical Research Institute. David has a keen interest in improving the way that we communicate science and educate and train scientists, including launching the Black Hole and writing for the Signals blog on regenerative medicine. If you're curious to learn more about the latest research on genetics and stem cell biology, you need to listen to this episode. In just a moment, the one and only Dr. David Kent. David, welcome to the RNT podcast.
Thank you very much, Gavrilo.
Let us start with basics. Where are you currently and what are you doing?
My name is David Kent, and I'm based at the York Biomedical Research Institute at the University of York in the Department of Biology. And right now, I run a scientific research group, and that group studies blood stem cells and how these blood stem cells are regulated and how they turn into cancers in people.
When did you originally take interest in science?
So I guess growing up, I was mostly encouraged. I come from a very small place in Canada, and the sort of jobs that we were encouraged to think about were lawyers, doctors, engineers, these sorts of standard jobs that people think about. And so I didn't really even know what a scientist officially was for quite some time. And so I went to university and really fell in love with the sort of problem solving that went along with science. And that's really where it sparked for me. And so I was always interested in sort of helping people with whatever I do, and scientific research really fit that bill for me.
It's quite interesting that you say that nobody was mentioning from elderly or from the side of your parents and neighbors that you could potentially pursue a career in science. It's usually, I think, everywhere around the world that people first come out with the proposals that you should become, lawyer, doctor, as you mentioned before. What do you think is the real cause behind that? Is the fact maybe that people are, coming out there with the obvious proposals and the most lucrative proposals, call it like ever you want, or do you think the problem is that people don't think of the science profession as something where we should be putting our children more into, or should be guiding them more into this profession?
Yeah, I think partially it's a generational thing, but most people don't really have a sense of most careers, right? So if you ask, a 14-year-old what it was to be a financial consultant, they'd also have no idea, right? And so I think we sort of have this allegiance to the standard careers. Everybody knows what a teacher is, what a nurse is, what a doctor is, because they sort of see these people and interact with these people. And there's loads of jobs. You would probably not encourage your children to be a professional dancer either, but then you find that they have the aptitude and you encourage them in that direction. So I would say my parents were very encouraging of whatever I wanted to do. But it just needed time to grow into becoming a scientist. That didn't happen until probably my 20s.
I think that's a great point that you just mentioned, because people usually go for something that is graspable, that is tangible. And if you never met in your lifetime someone who is a scientist, obviously it's quite difficult to get accustomed with what they're doing and why they're doing what they are doing. You're a parent yourself as well. When you go to a playground with your children, you're obviously rarely going to meet someone that is immediately going to tell you, oh, what do you do for work? As an answer to what do you do for work, that they will say, I'm a scientist.
Yeah, absolutely.
Unless they are you and you're with your children on playground.
Fair point. Or unless I started my career research-wise in Cambridge, and there you have a pretty good chance, actually.
Well, I would actually argue that over there is the other way around. So different animals are people who do something else and are not involved in research over there.
Yeah, absolutely.
David, why did you decide to focus on genetics specifically in your scientific research?
Yeah, so I went into in North America. We had these quite flexible programs. So I did my degree at the University of Western Ontario near Toronto, and I went into a degree that was basically it was genetics and English literature, and I didn't have to choose my genetics specialty until the third year of my degree. So I was in a sort of generic biosciences kind of program, and so that allowed me to sort of go through university level training and then choose what excited me the most. And the thing that really drew me to genetics, I think, was that it was much more about problem solving than it was about memorization. So I always found biochemistry and molecular biology quite attached to molecules that you had to remember pathways, and it was just that's what you had to report in your tests, whereas the genetics courses I had, at least, were very much about how would you experimentally discover this or that, and those were really exciting for me, that science could be much more about memorization, or much less about memorization and much more about problem solving.
That's quite interesting. So I'm someone who is pretty much for most of my life focused on let's say social science, less compared to other types of sciences. And I could definitely see that from your point of view and the point of view how science is taught is pretty much that you should try to solve the problem and then learn from the experience of trying to solve that problem. And that is how you're going to build to that level when you're actually going to be able to have some concrete solution.
Yeah, I think that's really important, and science is certainly a team sport these days. We don't make scientific discoveries in isolation, so it's about getting together with groups of people that you enjoy working with, and trying to tackle big issues, and trying to come up with new ways of finding out how to tackle those issues. And so that's just really exciting.
I fully agree with that. Just I think last week or the week before last, I actually listened to a TED Talk by Stephen Johnson, who is one of the most popular historians looking at the history of innovation, who basically said that whatever was innovated was not innovated by one person. It was always innovated by a bunch of persons throughout the long history or through a certain longer period of time, which kind of makes sense because in the end of the day, it's not just the team you are working with, but also teams that worked before on some elements of your research, and together with their past experiences and knowledge, you're going to be able to come up with your own innovative ideas and innovation.
Yeah, absolutely. And I think there's a real movement right now towards trying to make sure that the scientific record is really rigorous. And so there's a lot of, you'll hear things about data reproducibility and sort of integrity of the research enterprise. And I think those things are really important because, as you say, we're only as good in a project as the people who've come before us. And so we need to have that record be as good as possible in order to build effectively from the work of others. And so I think those movements are really important.
I agree absolutely with that one. David, in your genetics research, your focus is currently on malignant blood stem cell biology. Why did you decide to focus on this in your postdoctoral research?
Yeah, I think for me, there are lots of things that I could get into that would be really exciting because, again, it's about understanding how something works and understanding that for the purpose of having some sort of benefit for humans. And so I sort of stumbled into cancer biology through an interest in stem cell biology during my PhD. And so then when I was undertaking my postdoctoral work in Cambridge, so this is a period of protected research time, I really tried to add that branch of sort of human health more concretely. And so I think it's really fascinating the tools that have been developed to do sort of whole genome sequencing, understanding the molecules that drive cells at the single cell level and even the single molecule level now, to be able to really think about blood stem cells as a tool to make unlimited blood cell products outside the body. So things like cellular therapies, gene therapies, getting rid of blood cell donations for all of the communities across the world. Those would be incredible clinical advances. And then the other thing is to understand how stem cells go wrong in people. because of course a lot of the leukemias that kill people are derived from one single stem cell. So what happens to that cell and how does it get corrupted to drive a cancer is a really fascinating process. And so we try to use our understanding of normal blood stem cells to really advance our understanding of malignant blood stem cells. And so you need to have that fundamental understanding before you can start asking the fancy questions about how it goes wrong.
That is why my next question is pretty much a general one. What have we observed so far by studying and learning from all the studies that have been so far completed on the issue of genomes and genetics?
Yeah, so I guess us personally, one of the probably biggest impacts we've had was we took a set of clinical samples from diseases that are sort of precursors to leukemia, and we could show that the order in which you acquired genetic mutations determined quite a lot about your disease phenotype. So the sort of progression of your disease. So people who had one order versus the other order showed up an entire decade earlier in clinic with symptoms of the disease, and they would respond to drugs differently because of the order in which they'd acquire the mutation. So you would have cohorts of patients who have the exact same two genetic changes, but they have completely different disease phenotypes based on which one came first, basically. And I think that really set a precedent for the cancer field to be able to sort of ask those questions. Is that also true in colorectal cancers or breast cancers and these sorts of things? And this is why we use the blood system to study cancer biology, because it's really about that sort of easy to access model that's genetically not so complicated. So we can ask those sorts of fundamental questions in a relatively simple system.
Now, as you mentioned it, I also recall that recently I have read about the new blood type tests or blood tests that will actually be used to recognize the thousands of types of potential cancer cells in the body. Is that the future? We'll be able to observe and learn from those tests and pretty much use them to discover not only if a patient has a cancer cell in her or his body, but also if there are any new or other types of cancers out there that we are not aware of currently.
Yeah, so there's a really there's two things I'll say here. The first is about something called circulating tumor cells. So there's a lot of people talking about these things as liquid biopsies. So you can take a blood sample and see evidence of cancer cells having come from different areas of the body because they sort of break off the tumor that's forming in your prostate or in your breast, and they end up in the circulation. So they're very rare, but sequencing technology is at the point where you can look for these mutations and see if they're present, look for these cells and see if they're present in the blood. And so this would allow, instead of having to take a sort of chunk of tissue out of someone's prostate to do a proper full-fledged analysis, you might get some indication of that disease having been present in that person at some point. The other thing is that I think there's emerging evidence across a huge number of fields, but mostly related to cancer biology, that many of us have these sort of precursor genetic mutations that would lead to cancer quite early in life and quite frequently. So people have P53 mutations very commonly in many different cell types of their body. And so why some people end up getting a cancer that evolves from that initial sort of pre-cancer state and why other people don't is a great mystery. But certainly we can't be treating everyone as if they're going to develop cancer, because then there'd be an unnecessary burden of treatment. So it's really important to be able to determine who will actually get the cancer with great confidence versus who won't and should just be sort of monitored over time. But yes, I think there's going to be a huge amount of effort going into doing this rapidly with blood tests and doing this really cheaply so we can get it in more locations across the world.
That's a great point you made out there. So it's not only the precondition, it's how precondition develops in the end of the day, to which obviously things like lifestyle, smoking, drinking, heavily drinking, etc., plays quite a big role.
Yes, and I think that when I talk to physician colleagues, so I'm not a physician, but I talk to a lot of people who are oncologists or hematologists, and many times they say that their advice to people is pretty much the same as it has been for decades, which is you should lose maybe 10 or 12 pounds and should eat a little more healthy and do more exercise. And so it's, it's really quite funny that these are the common sort of trends in how to keep yourself generally healthy.
And then we had all those lockdowns across Europe where people pretty much stuck to their homes, and then they started to eat and put some extra pounds during the last 18 months of the COVID crisis, which is kind of ridiculous because if you look at the data, obviously nations that are for years or for decades, I will not say for centuries, had issues or are having the issues with the obesity, they're suffering the most from the current COVID crisis, which definitely tells you that you need to stay fit. And the only way that you can stay fit pretty much is going outside. And if you're not permitted to do that, then pretty much will be potentially after this crisis facing another crisis of obesity or cardiovascular diseases.
It will be very interesting to see. And a lot of people, of course, have also sort of one good thing is probably getting rid of commutes. So, driving in your car for an hour each way is a lot of people have discovered that's not what they want their life to be like. But equally, if we are going to be sat at home, we need to find ways of staying active, and it's going to be really important if we're not physically moving around to either go to meetings or serve customers or what have you. So I think that's going to be a big transition. You're right.
I fully agree. So it is definitely going to show us what we learned or what we did not learn. And it could be that we discovered that we still did not learn that we need to stay active one way or another because it's important not only for our physical but also for our mental health.
Indeed.
David, I just want to get back to one point that you mentioned earlier regarding the liquid biopsies and similar issues. Obviously, when you mention new types of tests, especially in relation to COVID pandemic, a lot of people have comments like, okay, maybe that's not accurate or not. But just recently, I had a look at one article that is comparing something called lateral flow test that you guys have over in the UK compared to the rest of Europe where they use other types of tests, and where they actually said that those tests are 80-90% correct. And not only that they're correct, but they also can determine if you actually have COVID in your system, in your body, at the right moment, compared to PCR that actually also catches the fragments of COVID that you could have had like a month ago or a few days ago, but that you have recovered in the meantime. And then based on those results, you're maybe banned from going into the airport or traveling to foreign country, despite yourself being vaccinated or having recovered from COVID previously. It's quite interesting, and I will just wrap up what I was saying by asking you a question on that one. How shall we convince people that tests are something that we need to do, and how we should convince them that if the results are maybe bad for them, that does not mean that results are 100% accurate, or on the other hand, that those results should be taken with caution and maybe potentially offering them a second a test or second piece of advice.
Yeah, I mean, this really it's a question for public health officials, and they put a lot of work into trying to get that information out accurately. But one thing to say is no test will ever be 100% accurate. The benefits of LFD testing, the lateral flow devices, is really that it's really quite simple and you can do it at home, and so that lowers the barrier for people to take a test. And so if you can do it at home in the comfort of sort of your surroundings and get that rapid result, it's no guarantee that you don't have it if you get a negative test. But if you get a positive test, it encourages you to be a little bit more careful. It encourages you to go get a PCR test or see a physician, and these are important things. So I think there's many different ways because we're battling different problems, right? One is accuracy, but another is compliance, right? And so will people even take a test? And you want to lower that threshold as well. So I think testing is critical, but you should turn to the sort of health officials for sensible and measured information about it. I mean, we're in a period now, I guess, where we have a lot of testing information and historic results, and this is where you refer to that study. They've sort of now been able to compile a lot of information about lateral flow testing and make these sorts of statements. But in the first sort of wave of the pandemic, nobody had any idea really about the accuracy of these things because they were still collecting the data. And so I think again these sorts of public health agencies, and they don't always agree in different countries, are places to get that sort of that information.
David, will stem cell therapies become a reality in the short term future?
Well, stem cell therapies are a reality already, which is quite good. We've been doing bone marrow transplantation since the 1950s, and they are effectively a stem cell therapy where blood stem cells go in and basically recreate the blood system in a host that is different from the donor. And so those are quite miraculous in their own way. But of course, I guess you're referring to that sort of stem cell therapy where we could be thinking about regrowing somebody's liver, or you have you're blind and you can regrow your eye tissue or the surrounding tissue and make yourself see again, and these are still reasonably experimental, but there's been incredible progress in certain diseases. And so I think there's probably not going to be the sort of cure every disease possible through stem cells, but you will see almost certainly over the next 10 years more and more stem cell therapies available for people. The important thing there is to really assess the provider of the stem cell therapy and make sure that the provider is a trusted authority and is based on real scientific information and real clinical trials, because that's where a lot of stuff goes wrong. And the International Society for Stem Cell Research actually has a really excellent set of resources around this, the types of questions you should ask a provider, the types of data you should be looking for. And it's really helpful for patients to be able to go there and ask those questions and see how they should be asked and what sort of information will keep them safe.
It is also important that patients are aware that that is future, and if they support future, obviously there will be more funds put into research on this one. We'll be getting better treatments, and then the cost of treatments will also go down. As it was with
Absolutely.
genomic sequencing, where we actually had costs that were like, I believe, and you can correct me that one because it's also part of your work, that the cost of one genome sequencing in the beginning of 2000s was approximately 1 million euros, pounds, or dollars, and now you can get genome sequenced at the cost of approximately $600. And that would not have happened unless people started studying genome and trying to learn from what was being sequenced.
Yeah, and I think an important point in there as well, and you may not know this, but the Human Genome Project, which started in 1990, it actually dedicated a percentage of every research funding package that it gave to scientific outreach to teach people about genomes and DNA. And these were really important in building that public trust and building that support for research. And as you say, the costs of genomic sequencing, because of these advances in technology, have come down incredibly far. I mean, we're doing genomes for even less money than you described now in collaboration with the Sanger Institute, and it's incredible what we can do now, right? We can sequence in the same person, hundreds of the same genomes over and over and over again, really cheaply, and discover things that are going on in patients that we had no idea about before. And this is where I mentioned earlier these sorts of these pre-cancer mutations. These are the types of studies that these discoveries are coming from, that advance in genomic technology, making it cheaper and more accessible.
David, we already touched base on COVID crisis, but we cannot move forward with our conversation without asking your personal opinion on how actually sexy the topic of genes and genetics in total has become since we have started living in the new normality called COVID crisis.
Yeah, so I think biomedical science in general has received a really great deal of attention through the COVID crisis. In particular, new technologies to make vaccines has become very uh, important and engaged with across society. And I think it's also important to say it's maybe not so much genetics, but immunology has really taken off, right? And so the interest that we see at the undergraduate level and people wanting to understand viruses and understand the immunological reaction to viruses is astounding. So we're training more and more people to think about this, and of course I think you're right. They've been captured by this sort of wave of information. People are starting to understand more about the immune system in the public, and they're starting to get curious about how we might use the immune system to sort of make human health better. So I think that's really exciting. Because it does mean that more people will start to choose to go into scientific research with hopefully the idea of preventing the sort of worldwide impact that we've had with this coronavirus crisis from happening again at this scale.
we're actually now jumping to the topic that I would like to discuss, and that's future pandemics. How do you think the sequencing of genomes of not only COVID virus, but what has been happening over the last, especially 30 years since the start of Human Genome Project that you mentioned during our conversation past minutes ago? How do you think what we have learned so far in terms of genome sequencing and genome learning, as I would call it, will help us prevent or easily mitigate future pandemics?
Yeah, so from a pandemic sense, I remember when SARS, the sort of original, happened, and this was when I first started my PhD, um, and and sequencing that genome took months, right? It really took a long time to get the SARS genome, and it was actually done first in British Columbia in Canada, and that's where they managed to sequence it. Um, and I think now, I mean, coronavirus, the COVID-19 SARS variant, it was sequenced in a matter of a week, right? Once people isolated it, it was just done instantly, basically. And so with that comes an understanding. It allows PCR tests to be developed. It allows vaccines to be designed. I mean, all of the mRNA vaccines are designed with the sequence in mind. The variants that you all hear about across the world, they're again found through genome sequencing, and it's because it's really cheap to do, and it's really available to most centers across the world, and so you can track variants not just in sort of the UK and the US and whatnot, but you can track them everywhere at a relatively cheap cost. And so I think that genomic technology has really revolutionized our ability to track viruses and understand how they've evolved over time and understand potentially where they're going to next. And that's going to be probably really important to get our heads around.
In terms of where viruses go next, what is your personal prediction on the COVID crisis? Will COVID kind of disappear or merge with other viruses like Spanish flu did? Which is quite interesting and something that amazes me since I learned a few months ago that pretty much Spanish flu is part of our regular seasonal flu since 1920s, and most of the people do not know and think that it's a disease that pretty much disappeared in the end of the day.
Yeah, so I mean, I'd leave the specifics to the virologists who study this properly. But I would say that this is certainly not the last thing we'll see. There will be new viruses emerging. They will come from different hosts, and I think what we should do and could do to prepare best for that is think about how we respond to a new virus. And I think that countries in Southeast Asia, as an example, because SARS, like the original version of SARS, was that broke out in 2005, was so much more serious there. They had a much better battle plan this time around for that initial wave. And whereas I think that in the UK we were probably quite slow to react and manage the spread of the virus initially. And so I think there we've got quite a lot to learn, but we'd be silly to think that there's not more viruses coming down the in our future. It's about how we respond to them, though.
I fully agree with you, obviously, because of the two trends, and that is that people have never more in their history been interconnected, have never more traveled between the continents. I mean, when you look at it, for 500 euros, you can pretty much travel from Europe to across half of the world, whilst 20 years ago, the situation was a bit different because the plane tickets costed more. And then also, people are living more closely with animals, especially in Asia, and that is how the viruses can be transmitted quite fast.
Yeah, I think human behavior does have a lot to do with it, and like you say, there's a lot of transit. When you think about an airport like London Heathrow or Frankfurt, these are big airports that have every country passing through them every day. So managing those sorts of things and shutting down airports is a big political decision. And but it had to be done for this one, and it could have and should have been done earlier probably. But of course, hindsight is 2020, right? We're very good at looking backwards and saying this is what we should have done. And those are hard decisions to make at the time.
David, what are the latest trends when it comes to the scientific research of genes?
Yeah, so I think it depends how recent you want to go, but some key things I think are the ability to manipulate genomes has been dramatically improved by tools such as CRISPR, which some of your listeners will have probably heard of. And so genome engineering has become quite exciting again. I think there's much better tools for doing gene therapy in people, so fixing genetic disorders where we know that there's a single gene that's causing a particular disorder. They're still quite expensive, but the technology is now emerging that we can fix these disorders in people in a lot of cases. So I think there's those are probably the two biggest areas where I think genetics has really started to have a real impact in medicine.
In terms of your scientific research, what is your current focus and on what exciting new projects you're currently working on?
Yeah, so I think one of the areas that we've recently moved into is we've developed a new technique based on whole genome sequencing of normal and patient-derived blood cells, where we can now start to enumerate the number of stem cells in a human, which is not really possible to do because we don't have the functional assays where we can transplant cells into human and do experiments. That's not how we do things, but we can now enumerate them without having to take them out, so to speak. We can just take a small blood sample and be able to do that. And once we discovered that we could enumerate stem cells and track them over time, we've started to do this in patients with diseases such as bone marrow failure, where some people basically develop a leukemia as a result of the selective pressures that are put on the cells that are still surviving in the bone marrow failure. And we can really track all of the mutations that occur in those patients, and we can track them over time for years to see which sort of stem cells are causing a cancer to grow and which ones are controlled, and try to design therapies around how we can target the ones that are sort of good for you, so to speak, and against the ones that are bad. And so obviously you want to target the bad ones and kill them off, and keep the good ones around so that your system can recover. So identifying which ones are the good and bad ones is really something that we're trying to focus on.
What are your future goals when it comes to scientific research?
Here, one of the biggest things is actually training people. One of the biggest goals that I have as an academic is to really create an environment where young people can test their ideas and explore new concepts and new things. So in many ways, your job as an academic, you become a sort of glorified fundraiser, right? You get the ideas together and get the grant money together so the young scientists in your lab can really push these boundaries. So we sort of set a strategic direction, but after that, it's really on the backs of young PhD students and postdoctoral fellows who are really pushing incredibly exciting stuff, and so it's a real treat to just watch them grow and explore those areas. That's probably the most exciting part of our jobs.
David, I'm really glad to see that you are pretty much jumping on the topic that I would like to address next. We touched base on this in the beginning of our conversation, but I would like now to learn more from you and your side activities when it comes to communicating science to the general public. How can we improve the way science is communicated, and how we can make sure that people understand what is happening in the closed doors of labs next door?
Yeah, so I think there's a couple of things. One is scientists need to learn to get out of their specialized language. That's one thing, because oftentimes it's not that the concept is hard; it's that the terms that are used are so specialized that it's like trying to speak German in as an English speaker in Germany, right? Like it's challenging because you don't know all of the words necessarily, and I think that's a real onus on the scientists to be able to sort of strip back their vocabulary so that people can have a broader understanding. But then I think it's important for us to be able to direct people to trusted sources of information. So not everyone's going to be able to go in and read a sort of article in Science or Nature magazine and understand everything. That's not what I'm talking about. Those are clearly reasonable, trustable sources. But we've got to police this sort of spreading of misinformation, and have people who want to get good information be directed to sort of safe and trustworthy sites where the information is compiled in a understandable and meaningful manner, so that people can get really easy access to important information that they can make their own important life decisions about. And I think coronavirus has actually been really good for this because people were desperate for information. They wanted to know daily, the numbers of cases in their particular region, and they wanted to track it over time. And this has really gotten a lot of people interested in how data gets collected, where the various pieces of noise are, and how dirty it can be in some places and how clean it can be in other places. And so I think that's actually, if you're looking for a silver lining, I think the way we've communicated science has really accelerated in a good way because of some of the things that happened in coronavirus early about misinformation spreading. It mobilized the science community to say, okay, well, we need to really focus on getting good information out there and attack the misinformation and make sure that people are getting access to the right information.
Unfortunately, a lot of misinformation is still happening, and people are kind of not trying to understand the facts, but believe in what they have heard or seen on Facebook or by googling.
Yes, yeah, and I think this is it's like any political sort of conversation that you have, right? You want to hear what you want to believe. And so if you want to have more freedom in coronavirus and be able to go out, you're going to actively find the data and the information that supports that decision and makes you feel good about that decision, which is perhaps quite dangerous. So I think it's really important that people have trust in public bodies that provide this information. But that's not a one-way conversation. The public agencies need to build that trust, and so the information that comes out needs to be accurate and not be overstated. And I think that's a real, like I say, it's a two-way conversation that needs to happen.
That's really great thing you just said. So I'm currently reading just a book about the negotiations and conversations between the people. And usually, the biggest problem we all have is that we focus in any conversations or negotiations on position of the other party across the table, whilst we should be focusing on substance. And I think both parties in this case are lacking that substance or focus on substance, because on one hand you have public authorities who want to focus on vaccinating the entire population, so we could move from this fluid space where there will potentially be new lockdowns to spread the to stop the spread of COVID or any new variants coming into reality sooner rather than later. But on the other hand, you have people who want more freedom but are not maybe willing to vaccinate themselves or to follow strict rules, and they're focusing on those positions and not on the substance. And the substance is pretty much that we will not have any kind of new normal, let's call it like that, until vast majority of population is vaccinated or has recovered from all possible variants, so we could reach that milestone of let's say mass vaccination or mass immunity that could support the herd immunity theory.
Yeah, I mean, all of these things are really complicated, and like you say, there's political forces as well as scientific forces and as well as public forces that all pull into this, and people have to make these decisions. That scientists don't always agree with the way that government would go about getting people vaccinated, but they would agree with the concept that we need to get more vaccinations. And so how the information gets spread, the government is trying to probably think about how do we convince people, whereas the scientific advisors would simply state the fact of it will be better if we can get more people vaccinated. So yeah, it's really tough, and there's lots of people in the conversation, and I don't know where to stand on that, because I tend to go with the scientists, but of course, when you actually need the goal at the end, not everyone's going to trust the scientists, and some people just don't like being told what to do, and so how do you get that cohort of people that don't like being told what to do something? It's really challenging, and so that is then not about the science, but how you communicate the science, and that's really challenging, and sometimes it ends up being a personal or a political argument that wins somebody over to the science and not the scientific facts themselves. And sometimes those have to be used to achieve, like you say, that sort of end goal of getting the scientifically based idea of having more people vaccinated accomplished.
I fully agree with you. I think the biggest problem is communication and misunderstanding in communication between all the parties involved in this issue, and it also kind of plays neatly with the current division culture, as I would call it, that we are currently having all across the world. People are divided on all possible issues and are just up for taking sides and not for really sitting on the table and making a fact-based decision.
Yes, I think that that's probably uh, maybe not just a recent phenomenon. I think there's generations of people that have had that sort of conflict, and it's really hard to encourage people to open their minds to the idea that a long held belief might be wrong, no matter what you're trying to put in. And the people who are trying to have those ideas often don't understand at all where that other person is coming from. And so again, I talk about these two-way conversations, really sitting down and wanting to understand the viewpoint, wanting to understand, not just trying to bring everybody onto your side, but trying to understand why they're not on your side, and maybe that you need to think about why your side might be wrong, so to speak. And these are all really hard things to do as humans, because we like to grab onto ideas, and we like to sort of share with people when we think we've got something that they don't know, and we like to, we want to, we're social animals, right? We want to help each other, and sometimes that help, however good intentioned, is sometimes misguided.
And that's, I believe, the biggest problem that you just mentioned, that people are kind of compiling and compiling sets of data and like you not using, but like stockpiling the information, thinking that we still live in the age of, let's say, information economy. But I think we are moving closely to the, let's say, stage of economy where we will have a knowledge-based economy, where it will not matter if you have a data, but how do you use data and what you make out of those data sets that you're storing somewhere on SharePoint or your P drives.
Yes, I think there's been a few little sort of explosions of activity in this space. There's been a few scandals and a few tech companies that have gotten in trouble, and you're absolutely right. How we use information is becoming incredibly important.
David, we went in all different kinds of directions, which is great. I always like to speak with someone who is a scientist like yourself and who also is working as part of your side activities on how do we communicate science. Before we ask you a few last questions, let me just ask you one thing that just came to my mind, and that concerns how the science will develop specifically in academia over the next, let's say, 10 years. Do you see more people coming to scientific studies? Do you see more people kind of engaging with scientists and then becoming scientists themselves after their doctoral, postdoctoral research work?
Yeah, I mean, there's a lot of, as long as we have problems in the world that require clever scientific solutions, I think we're going to be training scientists. They might shift maybe from biomedicine over to chemistry or physics or vice versa, but I think there's no end to the need for clever solutions to problems that face humanity. So I think we'll be seeing a lot of scientists grow over the course of the next decade and well beyond that. And so that the one trend that I would probably say is that science has certainly become more team based, and it's much less about the individual who discovers something, and it's much more about how do we compile the best set of experts across the world sometimes to tackle a big issue that goes beyond the capacity of a single individual or an individual lab. And so I think that people need to be open to interdisciplinary studies. People need to be open to different ideas, and just like you're trying to have that sort of political discussion we were talking about, sort of where you're trying to convince somebody. Sometimes you need to bring a mathematician on board with your biology idea. And that's kind of the same conversation. You have to open your mind to what the mathematician is thinking and how they're approaching the problem. And those are really educational sorts of interactions. And I think there's going to be way more of them because science is becoming so complicated and interdisciplinary.
I fully agree with you. So I think definitely that in the future we'll be having scientific teams of not people coming from the same field of studies, but from very different field of studies, and their knowledge, when you will put it together, will deliver some results that will in the end count the most.
Absolutely.
David, if I would ask you, and I'm going to ask you, what is the single most important thing that you love in your job? What would you say?
Well, I think I've already said it. I think it's the interaction with people, really sparking new ideas, growing that sort of young scientist into a scientist that can become an independent researcher. These are the things that are really exciting when you see the excitement and enthusiasm of young scientists coming in to try and tackle problems for the public good. I mean, and that's really, really rewarding part of our jobs.
David, any last words? Anything else that you would like to mention to the RNT audience?
I think your listener base is a really open minded one to be able to have the diversity of speakers that you've had on, which is really fantastic. And I hope that the trust gets its action in gear as well, because I know the missions that you're trying to achieve for education of young people are really, really important, and I hope that people will see the value in that, and I wish you all the luck in that. So please do keep in touch with me, with your network of scientists and social scientists, and engage with us, because we're happy to support.
David, thank you very much for your kind words, time, and thanks for being my guest on the RNT podcast.
Okay, great. Thanks, Gavrilo.